Welcome to Module 3, Algorithmic Bias and Fairness in Machine Learning. In this module, we move from the general idea that artificial intelligence systems can make decisions at scale into the more difficult question of whether those decisions are fair, reliable, and socially responsible. Machine learning models often appear neutral because they operate through data, mathematical functions, and measurable outputs, but the systems we build are shaped by human choices at every stage. The data we collect, the variables we select, the assumptions we encode, and the environments where we deploy a model all influence the kinds of outcomes that system will produce. A useful starting point is to recognize that bias in machine learning is rarely a single error that can be located in one obvious place. Bias can enter through the historical records used for training, especially when those records reflect unequal access, unequal treatment, or unequal institutional practices. It can also enter through incomplete or imbalanced data sets, where some groups' behaviors or experiences are represented far less accurately than others. Even when the data seems technically clean, modeling choices can still create unfair results because the model may optimize for accuracy in a way that hides important differences in who benefits and who is harmed. This is why fairness becomes such a central concept in responsible machine learning. Fairness is not simply a feeling that an outcome seems reasonable. It is a structured way of asking whether automated decisions treat individuals and groups responsibly. At the same time, fairness is difficult because there is no single definition that works perfectly in every context. A model might appear fair under one metric and problematic under another. So part of our work is learning how to evaluate fairness carefully rather than assuming that one number can settle the issue. As a result, the module asks us to slow down before accepting model outputs as objective. We will pay attention not only to whether predictions are accurate on average, but also to whether errors are distributed in ways that matter ethically. A model that works well for one population and poorly for another raises questions about representation, oversight, and use. Those questions are central to fairness analysis. Throughout this module, keep in mind that algorithmic bias is both a technical and institutional problem. The technical side involves data distributions, feature selection, model objectives, thresholds, validation procedures, and the way performance is measured across different groups. The institutional side involves the purpose of the system, the policies that govern its use, and the people who may have limited ability to challenge an automated decision. When those two sides are separated, organizations may produce systems that perform well on paper while still creating unfair or harmful outcomes in practice. As we move through the module, we will look at how organizations detect and measure algorithmic bias before these systems are trusted with real decisions. That means examining patterns in model outcomes, reviewing the quality and representation of training data, and using fairness metrics to identify whether certain individuals or groups are being disadvantaged. Data auditing matters here because it helps reveal problems that may otherwise remain hidden until the system is already affecting people. Measuring bias is not just a technical checkpoint. It is part of deciding whether a model is ready for responsible deployment. We will also examine strategies for reducing unfair outcomes and improving fairness over time. Bias mitigation may involve revising data sets, adjusting model assumptions, changing evaluation criteria, or putting governance processes in place so that fairness is monitored after deployment. This matters because machine learning systems do not operate in a vacuum. They operate in workplaces, schools, hospitals, financial institutions, public agencies, and criminal justice settings. In those environments, A biased model can affect access to opportunities, services, and institutional resources. So fairness becomes inseparable from accountability. The broader purpose of this module is to develop a disciplined way of thinking about algorithmic decision making. We are not treating bias as a vague ethical concern that sits outside the technical system, and we are not treating fairness as a simple compliance label added after the model is built. Instead, we will examine how bias, fairness, measurement, mitigation, and social impact are connected across the full life cycle of machine learning. By the end of this module, the goal is to understand that responsible AI requires both technical judgment and ethical judgment, because the consequences of automated decisions are ultimately experienced by people and communities. In this part of the module, we begin with a central foundation for understanding algorithmic bias. Machine learning outcomes are shaped by the data used to train the system. A model does not enter the world with an independent understanding of fairness, justice, or context. It learns patterns from examples that come from institutions with their own histories and limitations. When training data reflects unequal treatment, unequal opportunity, or unequal measurement, the model can reproduce those patterns with technical neutrality. A system may seem objective because it uses mathematical procedures while still carrying forward problems that began before the model was built. Bias can enter first through the quality, structure, and representation of the dataset. Quality matters because missing values, inaccurate labels, outdated records, and inconsistent measurement practices can distort what the model learns. Structure matters because the way data is organized determines which relationships are visible and which ones are hidden. Representation matters because some populations may appear frequently, while others may be absent, compressed into broad categories, or recorded in ways that do not capture their circumstances. The model then learns some patterns better than others, and that unevenness may not be obvious if we only look at overall accuracy. Historical inequality is especially important because many data sets are drawn from past decisions made by organizations, agencies, employers, schools, hospitals, lenders, or courts. If those past decisions were shaped by unequal access or unequal treatment, then the historical record is not simply a neutral archive of facts. It may contain patterns that reflect who was given an opportunity, who was denied one, who was over-surveilled, who was underserved, and whose outcomes were measured more carefully than others. A machine learning model trained on that record can treat those patterns as signals for future prediction. The danger is not random bias. The danger is that the system learns existing inequality as if it were a legitimate feature of the world. Incomplete data sets create a related problem because a dataset may leave out relevant cases, contain too few examples from a particular group, or capture only the people who interacted with an institution in the first place. That incompleteness affects what the system treats as normal, unusual, risky, qualified, or deserving. In practical terms, a model may perform well for groups that are heavily represented, while making less reliable predictions for groups that appear less often or are measured less accurately. Dataset representation is therefore not just a statistical issue, it is also an ethical issue, because the people least visible in the data may become the people most vulnerable to automated decisions. Modeling choices can also introduce or intensify unfair outcomes. Designers decide which variables to include, which target outcome to predict, how to define success, how to weigh different kinds of errors, and which performance metrics matter most. Each choice can have ethical implications, even when it appears technical. A variable may serve as a proxy for a sensitive characteristic or a target label may reflect an institutional decision that was itself biased. A model optimized only for aggregate accuracy may perform well for the majority group, while producing higher error rates for smaller or less represented groups. Design decisions matter because machine learning systems are built for particular purposes and used by particular people. A developer may decide where to set a classification threshold, how to rank results, how much uncertainty to show, and how much discretion a human user has when interpreting the output. These decisions can change the consequences of the same underlying model. A small shift in threshold may determine whether someone is flagged for review, denied a service, prioritized for assistance, or excluded from an opportunity. Fairness therefore requires attention to the full design of the decision process, not only the algorithm at the center of it. Deployment environments can amplify harm because the same model may have different consequences depending on where and how it is used. In hiring, healthcare, finance, education, and criminal justice, biased outputs can affect employment, diagnosis, lending, placement, surveillance, risk assessment, and institutional resources. These contexts involve opportunities and services that strongly influence people's lives. Bias can emerge across the entire machine learning lifecycle, from historical data to collection practices, modeling assumptions, design decisions, and real-world deployment. Responsible AI work requires more than asking whether a model is accurate. It requires asking whose data shaped the system, whose experiences were represented, and who may be harmed when predictions become decisions. Algorithmic fairness asks us to examine whether automated decisions treat individuals and groups responsibly when those decisions influence opportunities or institutional outcomes. This is not the same as saying that every person must receive the same result, and it is not the same as saying that a model is fair because it does not explicitly use a sensitive category. Fairness requires us to ask how decisions are distributed, how errors are distributed, and whether the system places certain people at a disadvantage. In machine learning, that question becomes complicated because the model may rely on patterns that are statistically useful but socially troubling. A variable can improve prediction while still reinforcing an unfair relationship. One reason fairness is difficult is that it can be defined in several ways. Some definitions focus on equal treatment, meaning that people who are similarly situated should be evaluated in similar ways. Other definitions focus on outcomes across groups, especially when historical inequality has shaped the conditions under which those groups appear in the data. Still, other approaches focus on error rates, asking whether false positives and false negatives fall unevenly across populations. These definitions are not interchangeable, and they can point us toward different conclusions about the same algorithm. This creates a major challenge because different fairness metrics may evaluate the same system differently. A model may show similar overall accuracy across two groups while still producing more false negatives for one group and more false positives for another. Another model may improve one fairness measure but worsen another, especially when the underlying base rates in the data differ across populations. In those cases, fairness cannot be reduced to choosing the metric that makes the system look best. Responsible evaluation requires explaining why a particular fairness definition fits the context in which the system will be used. The context of use matters because different decisions create different kinds of harm. In a hiring system, a false negative may mean that a qualified applicant is never interviewed, while in a healthcare setting, it may mean that a patient does not receive needed attention or follow-up. In finance, an unfair denial may limit access to credit, housing, or economic mobility. In education or criminal justice, the consequences may involve placement, monitoring, discipline, or risk assessment. Fairness analysis therefore connects statistical outcomes to human consequences. When we analyze algorithmic fairness, we are also asking who bears the burden of error. An institution may focus on efficiency, consistency, and prediction accuracy, but the people affected by automated decisions experience the result as access, denial, delay, stigma, or opportunity. This is why fairness cannot be treated as a purely internal model property. It has to be connected to individual impact and community well-being. A technically impressive model may still be unacceptable if its benefits are concentrated in one group while its costs fall disproportionately on another. At the same time, fairness analysis does not mean ignoring model performance. Accuracy, reliability, explainability, and fairness all matter, and these values can create tension. A system designed only to maximize prediction accuracy may overlook group-level disparities, while a system designed only around one fairness rule may miss other harms that occur in practice. Careful analysis requires holding these tensions together rather than pretending that a single equation solves the ethical problem. Fairness definitions function as tools for judgment, not as automatic answers. They help organizations ask sharper questions about automated decision-making systems, including who is being evaluated, what outcome is being predicted, which historical process produced the labels, which errors matter most, and who is most likely to experience them. These questions allow fairness metrics to become part of a broader responsible AI process, rather than a checklist added after deployment. The metric becomes useful when it is connected to the purpose of the system. Researchers and practitioners use fairness definitions to compare systems, diagnose problems, and decide whether a model is appropriate for a given setting. But selecting a fairness definition is itself a normative decision because it reflects what the organization believes that should matter in that context. In some cases, the priority may be reducing unequal error rates. In others, it may be preventing exclusion, protecting vulnerable groups, or ensuring that individuals are evaluated based on relevant criteria. Fairness in algorithmic systems therefore involves mathematical measurement, responsibility, accountability, and judgment about social impact. A fairness metric can clarify a problem, but it cannot replace ethical reasoning. Organizations detect algorithmic bias by examining model outcomes for unfair patterns, but that work begins before anyone looks at a fairness report. Bias detection requires us to ask what the model is doing, who is affected by its decisions, and whether the patterns we observe are acceptable in the context where the system will be used. A model can appear successful when measured only by aggregate performance, yet still produce troubling differences across groups. Responsible evaluation looks beneath the average and asks whether some people are more likely to be misclassified, overlooked, denied, delayed, or flagged. The first layer of bias detection involves data quality and representation. If the training data is incomplete, imbalanced, or mislabeled, the model may learn patterns that do not generalize fairly. Data auditing helps organizations examine whether groups are represented adequately, whether labels are reliable, whether missing data has a pattern, and whether certain variables are standing in for sensitive characteristics. This kind of audit is not just a housekeeping step. It is a way of asking whether the evidence used to train the system is strong enough and fair enough to support real decisions. Representation matters because machine learning models learn from the examples they receive. If one population is well represented and another appears only rarely, the model may become more reliable for the first group and less reliable for the second. That difference may not be obvious, if the organization reports only one overall accuracy score. A model with strong average performance can still produce higher error rates for smaller or less visible groups. Measuring bias therefore requires breaking performance down into meaningful categories and asking whether the system behaves differently across those categories. Fairness metrics support this work by giving organizations a structured way to evaluate whether outcomes disadvantage certain individuals or groups. These metrics may examine selection rates, approval rates, error rates, false positives, false negatives, or other patterns that connect model behavior to real consequences. The purpose is not to turn fairness into a single number that settles every question. The purpose is to make disparities visible so they can be examined, explained, and addressed. When a metric reveals a difference, it becomes the beginning of an inquiry rather than the end of one. One challenge is that bias can appear in different parts of the model's behavior. A system may approve people at similar rates, but make different kinds of mistakes across groups. It may have similar accuracy, but very different false negative rates, meaning one group is more likely to be incorrectly excluded from a benefit or opportunity. It may have similar false positive rates, but still rely on features that reflect historical disadvantage. Detecting bias requires more than checking whether the model uses protected categories directly. It requires examining patterns of impact, error, and decision quality. Measurement also depends on choosing the right comparison groups and the right outcomes. If the groups are defined too broadly, important differences may disappear inside averages. If they are defined too narrowly, the analysis may become unstable because there are not enough cases to support reliable conclusions. Organizations have to balance statistical validity with ethical attention to the people most likely to be affected. It also matters whether we measure accuracy, ranking position, denial rates, intervention rates, or downstream effects after the automated decision is made. Detecting bias is connected to deployment readiness. Before an AI system is used in hiring, healthcare, finance, education, criminal justice, or another consequential setting, organizations need evidence that the model performs responsibly for the people it will affect. That evidence should include technical performance, fairness analysis, data review, and an assessment of foreseeable harms. A model that has not been tested for disparate outcomes may be ethically unprepared for deployment. Responsible AI requires that organization understand system behavior before allowing it to influence real decisions. Finally, bias measurement should be treated as an ongoing process rather than a one-time certification. Data can change, populations can shift, institutional practices can evolve, and a model that appeared acceptable during testing may behave differently after deployment. Continuous monitoring helps organizations identify whether unfair patterns emerge over time. Data auditing, fairness metrics, and outcome analysis work together to create a disciplined approach to evaluation. The goal is not to prove that a model is perfectly fair. The goal is to detect unfair patterns early, measure them carefully, and decide whether the system can be improved enough to support responsible use. Bias mitigation begins with the recognition that unfair outcomes do not correct themselves because a model is technically sophisticated. Once a machine learning system has learned patterns from data, those patterns can become part of real decision processes unless they are examined and adjusted. Mitigation then means reducing unfair outcomes before deployment, during deployment, and throughout the continuing life of the system. It is not a single repair step added at the end. It is a disciplined process of looking at data, model behavior, organizational use, and human consequences together. The first practical strategy is data auditing. Before a model affects hiring decisions, healthcare recommendations, financial approvals, educational placement, or criminal justice assessments, organizations need to understand the data that trained it. Data auditing asks whether the dataset is complete, whether groups are adequately represented, whether labels are reliable, and whether historical inequalities are embedded in the records. It also asks whether certain variables may act as proxies for sensitive characteristics, even when those characteristics are not named directly. This kind of review helps identify sources of bias early, before people experience flawed decisions. Auditing also requires attention to how the data was collected. A data set may look large and detailed while still reflecting narrow institutional practices or uneven measurement. If one group was historically observed more closely, reported more frequently, denied access more often, or classified according to different standards, the model may treat those patterns as predictive signals. In that situation, adding more data does not automatically solve the problem. The organization has to ask whether the data is appropriate for the decision being made, and whether it carries assumptions that should not be reproduced. Fairness metrics provide another important mitigation tool because they help organizations evaluate whether model behavior aligns with responsible AI goals. These metrics can compare selection rates, error rates, false positives, false negatives, calibration, or other outcome patterns across groups. Their value is that they make disparities visible and measurable. However, fairness metrics should not be treated as mechanical approval stamps. They are most useful when connected to the system's purpose, the kind of harm that matters, and the responsibilities of the organization using the model. Once unfair patterns are identified, model adjustments may be necessary. These adjustments can involve changing the training data, revising the target variable, removing or transforming problematic features, reweighting examples, adjusting thresholds, or selecting a different modeling approach. Sometimes the issue is not that the model is broken, but that it is optimizing the wrong objective. A model may be good at predicting a historical outcome, while that outcome itself reflects unfair institutional practice. In that case, mitigation requires more than technical tuning. It requires reconsidering what the system should be trying to predict. Threshold decisions are especially important because they often determine how predictions become actions. A probability score may not directly harm anyone until it is used to approve, deny, flag, rank, or prioritize a person. Changing a threshold can reduce one kind of error while increasing another. So mitigation requires careful judgment about which errors are most harmful in context. In healthcare, missing a person who needs care may carry different ethical weight than providing an unnecessary follow-up. In hiring or finance, an incorrect exclusion may have long-term consequences for opportunity and mobility. These trade-offs should be made openly, not hidden inside the model. Governance is what keeps fairness from becoming a one-time technical exercise. A model may pass an initial fairness review and still behave differently later because populations shift, deployment settings change, and new data may drift away from the original validation conditions. Organizations therefore need documentation, monitoring, periodic audits, escalation procedures, stakeholder review, and clear responsibility for addressing problems when they appear. Governance also creates a structure for deciding when model adjustments are required and who has the authority to revise a system that produces unfair outcomes. The broader goal is not to claim that a machine learning system can be made perfectly fair once and for all. The goal is to build systems that are evaluated, corrected, monitored, and governed in ways that reduce unfair outcomes and support responsible use. Bias mitigation brings together data, auditing, fairness metrics, model adjustment, and organizational accountability. When those strategies work together, fairness becomes part of AI development rather than a label applied after deployment. The societal consequences of biased AI decision making are significant because automated systems increasingly shape access to opportunities, services, and institutional resources. When a biased model is embedded in hiring, healthcare, finance, education, or criminal justice, the effects can become concrete very quickly. A prediction can influence whether someone receives an interview, qualifies for a loan, receives medical attention, gains access to academic support, or is classified as risky by an institution. It becomes part of how power, opportunity, and disadvantage are distributed. One important point in this module is that biased AI decisions can affect people even when no one involved intends to discriminate. A model may be trained on historical data, optimized for efficiency, and deployed with the belief that it will make decisions more consistent. Yet if the underlying data reflects historical inequality, the system may reproduce that inequality through apparently neutral predictions. The danger is that automation can give old patterns a new form of authority. What once appeared as a human or institutional judgment may now appear as a data-driven recommendation, even when the underlying pattern remains unfair. Hiring provides a clear way to understand this consequence. If a model learns from past hiring records, it may learn the preferences, exclusions, and assumptions embedded in those records. Qualified applicants may be ranked lower because their experiences, schools, career paths, or employment histories do not resemble the patterns most strongly represented in the training data. The model may not explicitly say that it is disadvantaging a group, but the effect can still be exclusion from opportunity. In that setting, fairness matters because employment is connected to income, mobility, stability, and development. Healthcare raises a different but equally serious concern because biased systems can influence care, diagnosis, prioritization, and resource allocation. If certain populations are underrepresented in medical data, or if past access to care shape what was recorded, a model may become less reliable for the people who already face barriers. A biased recommendation can delay treatment, underestimate need, or misdirect attention away from vulnerable patients. In healthcare, model performance cannot be judged only by technical accuracy. It must also be judged by whether the system supports equitable care and human well-being. Finance and education show how algorithmic bias can influence life chances over time. In finance, biased credit or risk models can affect access to loans, housing, insurance, and economic opportunity. In education, automated systems can influence placement, intervention, advising, discipline, or access to support services. These decisions may look small when viewed one at a time, but their effects can accumulate. A biased decision at one point can limit future options, and a pattern of biased decisions across institutions can reinforce inequality across communities. Criminal justice is especially consequential because automated assessments may affect surveillance, sentencing, supervision, detention, or release decisions. In this context, errors carry serious personal and social costs. A false positive may lead to unnecessary restriction or increased monitoring, while a false negative may be treated as a public safety concern. The ethical challenge is not only whether the model predicts accurately, but whether it reproduces patterns from policing, charging, conviction, or sentencing data shaped by unequal institutional practices. In high-stakes settings, fairness and accountability must be essential. The societal impact of biased AI also includes the way institutions may rely on systems that are difficult for affected people to understand or challenge. when a person is denied a service or opportunity because of an automated output, they may not know what data was used, how the decision was made, or whether an error occurred. This lack of transparency can reduce the ability to contest an unfair result. Bias, therefore, affects not only the outcome itself, but also the fairness of the process surrounding that outcome. For this reason, algorithmic bias should be understood as a governance issue as much as a technical issue. Organizations need to ask who is responsible for monitoring outcomes, correcting unfair patterns, explaining decisions, and deciding when a system should not be used. Fairness, responsibility, and human well-being are central because AI systems operate inside social institutions, not outside them. The purpose of responsible AI governance is to prevent automated decisions from reinforcing historical inequality and to ensure technical systems remain accountable to the people and communities they affect. Fairness is not an accessory to machine learning. It is part of whether machine learning can be trusted in real human contexts.